Or we actually pump the water in high altitude, and when the energy is required for the peak demand, then we actually generate electricity from it. So in our research, we will be focusing on mainly this impoundment reservoir. So as you can see, the world's energy demand is ever increasing due to demographic expansion, economic development, and urbanization. So 1/6 of the electricity in the world comes from the hydropower, surpassing the nuclear energy and other renewable sources combined. So more than 150 countries are now working with the hydropower sector, and China, Brazil, USA, Canada, Russia, and India, they are the top hydropower producers in the world. So India possesses hydropower installed capacity of 51,785 megawatt as of 2022 reports, and which leads to a total generation of hydropower like 174.5 terawatt hours as of a report of 2022. So we want to be focused on what are the advantages of these hydropower reservoirs. So we all know they are the source of our renewable energy. We can have the flexible power generation from them. Energy storage, we can actually have discussed about that. Long lifespan and durability, flood control, water management, water supply and irrigation, and recreation and tourism. So these are basically the advantages of hydropower reservoir. But there are some environmental impacts of hydropower reservoir. While generating clean energy, they can actually disrupt the ecosystem services, as we can see in this picture also. And most interestingly, recent studies have actually proven that they are the potential emitters of greenhouse gases. So these greenhouse gas concentrations are intensifying their catastrophic consequences, like on climate extremities, rainfall pattern, sea level increase, water quality, etc. So what is the importance of mitigating these methane emissions? So greenhouse gas impact, so we can actually reduce the greenhouse gas impact. Then climate change mitigation, air quality can be improved. Then we can actually protect our ecosystem services, inhibit positive feedback loop. So we can actually say in the permafrost there has been frozen methane hydrates. So increasing temperature can actually cause more methane to be in our environment, and further amplifying the global warming. So this will actually create a positive feedback loop. And there are economic benefits if we are talking about the circular economy. What is the process of greenhouse gas emission from the reservoir? So when we are actually building a dam, so we are inundating the vegetations over there. And when these vegetations, like these organic carbons, are being sedimented, and an anoxic zone is formed here, so we can actually see the CH4 is being liberated from here. And as of the researchers till now, we have actually found that there are 4 pathways of these emissions, like CH4 bubbling emission is there, diffusive CO2 and diffusive CH4 are there, and CH4 degassing emission in the downstreams are there. Okay. So these are the driving factors. Like for CH4 degassing, you can see we have connected like annual runoff, catchment area, this reservoir area. They are actually connected with the CH4 degassing emissions. Then CH4 bubbling and CH4 diffusive emissions are also being connected like similar ways. You can see the max depth is actually going to the littoral area, and it is further actually connecting to CH4 diffusive emission, and this CH4 diffusive emission is again connected to the CH4 degassing emission. So we can actually say these are the driving factors, mainly related to CH4 emissions. And next we have the CO2 diffusive emission. So soil carbon content, LULC, annual runoff, catchment area, these are contributing to phosphorus concentration, and then it is again contributing to the CO2 diffusive emissions. So they are connected like this. So this is a very interesting thing. We have done the bibliometric analysis. So we have fetched 470 articles from Scopus database using this following syntax like GHG, greenhouse gas, hydropower, hydroelectric, hydropower, or. Okay, so by this syntax we have got 470 articles globally. So we have plotted this temporally, like year-wise publication trend, we can see it is increasing. And here we have actually plotted the spatial distribution of the papers. Like you can see in the China, Brazil, these areas are having more than 40 papers, publications are there. And the very much interesting thing is, when we are just adding the remote sensing aspect to this previous index, like we are using remote sensing or GIS or geographic information system, so this actually reduces this articles number significantly to only 18. So this is actually showing that the newness and the huge research gap in this domain. So next, we have done this analysis using Boss Viewer. So you can see here, these are the main keywords obtained from these 470 articles that we have fetched from the Scopus. And if you are clicking in any of this, like if you are clicking in this hydroelectric reservoir part, so then it is showing that what are the other related keywords they are closely related to. So we have actually made this visualization total link strength and 15 co-occurrences of all keywords has been actually studied to make this visualization part. And like we have discussed about that 18 documents, so these are the main 4 documents that I feel important for our study, and I have actually gone through them. The major research gap on these papers are actually, they are not discussing about the dynamic nature of the reservoir. Like we all know that hydropower reservoirs are dynamic in nature. They can be altered, like if we are changing the water level, the water extent is going to change, and it is going to affect the other parameters what are actually influencing the GHG emission from these reservoirs. So this study is need to be done. Here is one research gap we can actually identify. Secondly, we can say the reservoirs from different climatic zones are not being studied yet. So we can actually go for the different climatic zones reservoirs, then we can actually study this. So there is a huge research gap you can actually identify. And most importantly, in India there has not been any comprehensive work till now. So it actually showing you that how much research gap is there. So if you, any one of you is wanting to work in this domain, you can go for this. So this is the overall basic methodology what we are actually using. So we have GE database. My previous speakers like Orkon and Punit, so they are actually explaining the utilities of Google Earth Engine. So you have actually seen there are so much free data are available in Google Earth Engine. So we are using Google Earth Engine database, and we have actually modified a Google Earth Engine code. So this Google Earth Engine code will help us to derive some Google Earth Engine derived parameters that are going to be used in the GRSS tool, and this GRSS tool in exchange will give us the estimated GHG emission for that 4 pathways that we have discussed earlier. Okay, so as of GRSS tool, we will discuss it later. So then this estimated GHG emissions will be stored in our system storage, and then we will go for the further analysis in our system. So let's see what is actually, in Google Earth Engine, I have talked about the GE derived parameters. So there are basically 4 GE derived parameters. We can actually classify them as catchment data, reservoir data, climate data, and buffer data. So here are the catchment data. What are we going to need in GRSS tool to calculate the GHG emission? So you can see to get this catchment mean annual runoff, we are depending on these 2 databases primarily. You can see the connections. Like GRND database is there, and one composite runoff database in paper Pickett et al. It is mentioned. So these 2 databases are used. Like to have the catchment population, we are using this GRND database and this CIESIN database. You are well known of, I guess. Then to get the catchment land cover type by soil, so we are using this ESSECI database, this GRND database, and this UNESCO IHA, there is a database. So we are using these 3 databases. So like this, the next reservoir data. So like the previous one, to get these parameters, we are depending on these databases from Google Earth Engine, reservoir data. Okay. Then if we move, so these are the climate parameters, what will be needed in the GRSS tool. And these are the databases that we are actually focusing to get these derived parameters. Then there are buffer data similarly. So next, what are the advantages of Google Earth Engine? So we are actually talking about Google Earth Engine like from yesterday you were just listening about Google Earth Engine, Google Earth Engine. So actually Google Earth Engine can provide us a huge public data catalog, as many of the earlier speakers has also discussed, like Landsat, we have got the access, MODIS, terrain, land covers, atmospheric NOAA data. So these all are available, and this could actually help us in our on-demand computation. This can reduce the human time, reduce the CPU cost, reduce the disk cost, and it is also very actually compatible with the batch computation. So it reduces the serving latency, you can see over here. So moving to the next slide, this is our GRSS tool, the homepage interface. So we have some physical quantifying techniques as of now to quantify GHG emissions. They are floating chambers, AD covariance, you can say, infrared gas analyzers, bubbling traps, ultra portable GHG analyzers. But integrating Google Earth Engine derived parameters with this GRSS can provide an edge in terms of feasibility and data producibility, as you all are aware of. So this GRSS tool is simple to use. It is a web-based tool that can actually use to predict the GHG emissions, and it has been developed by International Hydropower Association in collaboration with UNESCO. So actually what they have done, they have actually done their analysis for 223 reservoirs around the world for different climatic zones, and they have made empirical formulas for each of the parameters that we are discussing. So for if we are changing the climate, so their empirical formulas regarding catchment area, population, and the vegetation, they are also changing. Okay. So this is our Google Earth Engine interface. You are now familiar of, I guess. So this is the code. After running the code, you can get the data like this. Like it is showing reservoir data, dam latitude, longitude, area, river length before impoundment. So you can get the data like this. This will be charted over here, and you can go to this task panel, and there will be some CSV file format which you can actually download and copy paste in the Excel. Then you can actually use this data onto the GRSS tool to estimate the GHG emissions from there. So next, these data what we have fetched. So we need to input these in this GRSS tool like this. They have also these parameters landscape. So these are the GE derived data which we are providing in the GRSS tool. This is reservoir data, reservoir parameters, what we are actually filling. Then in turn, GHG emission is being estimated for by the GRSS tool. Like you can see, it is actually creating a report. So in this report, you can find your parameters, what you have actually provided. And here are the four pathways that we have discussed in the, like in the previous slide. The emission pathways for CH4 diffusive, CH4 bubbling, CH4 degassing, CO2 diffusive are there. And it is also estimating GHG emission for 100 years of time. Total GHG emission you can get over here. And so, what is the way to mitigate this GHG emission? We are talking about to estimate, we will be estimating this GHG emission. But what are the ways, possible ways, so that we can actually mitigate this GHG emission and reduce its consequences in our nature? So you can say changing operating level. So me and Surojit sir have worked for a paper, and Anubhadi is not here, I guess. So Anubhadi is also a co-author of this paper. So we have actually done extensive work, like how changing operating level is going to affect our GHG emission. So this paper has been selected in IEEE conference this year, 2023, and it is going to be published very soon. So if we are changing this operating level, interestingly we have found a 30 centimeter increase in Maithon reservoir of water level can decrease the GHG emission by like 7%. So it is a huge. Then another mitigation strategies could be adding a secondary intake over thermocline. So what is actually happening? These reservoirs are stratified. Okay. So thermocline, you can say, is here. So oxycline is another term which actually we can relate with thermocline. So if this oxycline is also lies with this thermocline, then the oxygen which are in the above layer of the methane cannot be mixed with this methane and cannot oxidize methane. And we all know that methane is a very potent greenhouse gas. So methane is having 34 times global warming potential than carbon dioxide. So if we can actually provide intake over here to the thermocline, so what we can actually do, we can actually pass the more oxidized water into the turbine so that it can actually decrease our greenhouse gas degassing emissions. Okay. So next thing we can actually talking about, we can talk about installing aerating devices for oxidization. So in world like in Laos, I guess Nam Thuyen 2 reservoir is there. So they are actually using this method to oxidizing their methane part and reducing the global impact of methane. So another strategy could be converting this methane emissions into energy. So it will be a win-win situation for us if we can capture this methane and can utilize this methane for energy production or transportation. So in Brazil, I can actually suggest you a paper. You can search Ramos et al. 2007 and 9. He has two papers. So he was actually talking about how we can actually capture this methane from the reservoirs and actually work further to develop a transportation or energy producing system. So these are some policies. So in our countries, if we actually want to mitigate these methane emissions, so we actually need some policies that will be connecting greenhouse gas emission with the reservoirs. So actually, in our countries, there are no specified policies till now regarding this greenhouse gas emission and reservoirs. So these are some policies that are actually connecting with reservoirs in respect of environment. Okay, like protecting environment, which are the policies we have actually in relation with the hydropower sector. So Wildlife Protection Act 1972 is there. You can say see the description, like it aims to protect the wildlife and their habitats, hydropower projects. Okay. So Water Protection Act 1974, Forest Act 1980, Air Prevention and Control Pollution Act 1981, EIA 1994, National River Conservation Plan 1995. These policies are there. Here are some other policies also. National Policy on Hydropower Development, Ganga. So actually we can go for some suggestion and modification with these policies so that we can actually in future we can actually go for the mitigation of these greenhouse gases which are emitted from these hydropower sectors. So what are the policy gap and associated policies we could look for? So in spite of all these initiatives we have mentioned, these India's hydropower and GHG emission policies are still evolving, we all know, due to the environmental, economic and technical issues. So to address these changes, India could actually enhance its environmental impact assessment policies and environmental, social and corporate governance ESG regulations for these hydropower projects in future so that we can actually monitor and mitigate GHG more efficiently. So in conclusion, we can say this while hydropower is a low carbon renewable energy source, so it is crucial to recognize that hydropower reservoirs emit GHGs. So they are no longer the super clean source of energy we are talking about, but we can actually go to make it more effective and clean energy source in the future. So recently the hydropower sector in India is mushrooming, we can actually see for the energy demand we are having in our country. So though the danger of GHG emission is notable, the present study showed that cloud-based tools like Google Earth Engine, GRSS, what we have actually discussed, integrating with the Earth observation data can be a useful tool for our estimating this CH4 emissions and further mitigating it in future. So in acknowledgement, actually I want to acknowledge NIT Durgapur from where actually I have done this research, and I am thankful to CGIAR also. So these are the references you can go for if you are interested. So you can click. So thank you. So now we will be having demonstration part, like how our actually this tool GRSS is working in integration with this Google Earth Engine or EO data, what we are talking about. So all of you have laptops so that we can actually hands-on.
So interesting, you forget about tea. They are only tea. Okay. Sorry? Half. Okay. So we have another lecture from from 4:15 we have another lecture. So if you want to take some rest, someone basically please mute. Yeah, thank you. So do you want to take rest? 5 minutes? Tea break? You have to come back by 4:10? Okay. So now I would request Vishwajit Pradhanji to come here and
Thank you so much, sir.
Hello. Let's thank you. Let's thanks Konik. 7 o'clock. Okay. So let's thank Konik for his nice talk on this greenhouse gases and its monitoring. So, so as Shad said, we have a break here, and there is a notification around 7 o'clock. We have a cultural group of IIIT is going to perform in our auditorium. So all are being invited to join there at 7 o'clock. Thank you.
so we will start our next session at 4:15 sharp. So we'll have Mukhtar from IWMI Ghana office. So I would say it's a completely different thing we will see, that how we can account water, so water accounting. And it will be a short presentation, but I think it will show us a different direction. Right. So be here before 4:15.
lies in hydrological modeling, water accounting, water resource assessment, irrigation, drought, climate change, remote sensing, and GIS. We would present the next lecture on water accounting plus under climate change with a case study in the Volga River Basin. The stage is open for you.
Thank you very much. I don't know who was talking exactly, but good afternoon, good evening, everybody.
This is Anubhav.
I'm Definitely from the International One. Okay, I'm Definitely from the International One Institute, where I work with audits. Today I'm pleased to take part in this workshop and make a presentation on the topic of water accounting plus under climate change. The case study in the water river basin, which is located in West Africa. For the sake of connectivity, I think I will disconnect my camera now and get the presentation, and I may turn it on later on for questions and answers. Okay, so let's start with this map, which shows that we are living on a thirsty planet. This map shows the spatial distribution of global water scarcity, and the redder the region, the most persistent the annual water scarcity. Here you can see that half of the world population is affected by water scarcity. A huge part of Africa and Southeast Asia is concerned. Before I proceed further, can you confirm that you can see my slides? They are moving? Alright, excellent. Excellent. That's it. Okay, then I'll continue the presentation. Okay, and we also know that water is a vital resource for life. But due to water stress in river basins, people live by an inadequate level of water security. Water scarcity has severe implications for many sectors, including agriculture, hydropower generation, and biodiversity. And once these sectors are affected, there are several severe consequences for the sectors like health, as well as the economic development. However, climate change is expected to exacerbate water scarcity, which thereby poses a lot of uncertainty regarding future water availability. And in some contexts, information on future water availability is essential to develop some policies for long-term water management. One of the tools for assessing and monitoring water resources is called water accounting. And according to the Food and Agriculture Organization of the United Nations, which describe it as the systematic acquisition, analysis, and reporting of information on water stocks, flows, and fluxes in natural as well as in disturbed or profoundly technically modified environments. Water accounting focuses on the analysis of trends in water supply and demand, and its accessibility and use in space and also in time. Water accounting makes it possible to answer some of these questions. For instance, is there an overexploitation of water resources in the basin? Is the water consumption really beneficial? For instance, the water that is being allocated to agriculture and what we are getting out of it, the product that we are getting out of it, is it really beneficial? Can we use less water to produce what we are still getting? And how can we better manage water resources at the basin level? There are different water accounting approaches or frameworks or tools that exist, which have been developed by different institutions over the years. So there are a couple of them. But the issue is that some of these tools have been adopted as a general standard, and they are not systematically applied in integrated water resource management. This is explained by the fact that these tools in general produce complex results that are difficult to understand by various water professionals, which do not facilitate the task of decision makers, for instance. And most of these tools require large amount of data, which limits their use in countries that do not have sufficient financial means for data collection and maintenance of the system. And also, these tools do not consider the consumptive clauses and return flows, and they do not explicitly link water flows and land use. Therefore, to address these constraints, a new water accounting tool has been created, and it's called Water Accounting Plus. So Water Accounting Plus is a framework that summarizes complex ecological processes, including water flows, stocks, and consumptions, based on standard reporting sheets and key indicators to describe water availability and uses in large-scale basins. The approach is based on the water balance with spatial analysis. It is developed to be implemented with satellite data, thereby making it suitable for data-scale region. It also explicitly accounts for interactions between water flows and land use. It also distinguishes between manageable and non-manageable flows, and assesses beneficial and non-beneficial consumption for various activity sectors. Therefore, Water Accounting Plus provides an independent and unbiased assessment of water resources, which is suitable for well-informed and transparent decision making. So this is an example of the Water Accounting Plus result sheets, and I was saying, when you do the Water Accounting Plus calculation, the overall goal is to summarize the result in a simpler format that can be used by decision makers. So this is an example of the results sheets of Water Accounting Plus in order to facilitate information understanding by decision makers. For instance, this resource-based sheet summarizes information on how much water is flowing into the system, how much water is lost to landscape evapotranspiration, how much water is available in the system that can be exploited, and then that one, how much is already being utilized, and how much is reserved for downstream countries, environmental flows, navigational flows, for instance. And after all that, how much water is still remaining in the system that we can further allocate to other sectors, including agriculture, hydroelectricity production, fisheries, navigation, and so on. So as I was saying, water accounting links water flows to land use, and it's also based on satellite remote sensing data. Then if we want to use Water Accounting Plus to do water resources analysis on climate change in the future, for instance, how can we do that? Knowing that the framework is developed to use satellite remote sensing data, and we don't have satellite data for the future. Therefore, let's make Water Accounting Plus a static framework, so no future scenarios. But how can we use Water Accounting Plus for water management under climate change? So the strategy that we do here is that we integrate a zoological model in the process with climate change scenarios, and then use output of that framework as input in the Water Accounting Plus framework. But one thing that is really important here that we have to make sure that is being done well is the accurate representation of processes, not only in time, but also in space. Because how you will see that the Water Accounting Plus is basically a spatial analysis where water flows are linked between that we need to make sure that the spatial situation of the flows and fluxes based by the analytical model are very well represented. So basically, I think the model is all about producing water cycle. And for that, there are different challenges that we face in doing that. For instance, the reliability of the meteorological data that we do to support the model. Sometimes the lack of in-situ mainly street flow data to calibrate the model, for instance. And also, another parameter that is sometimes overlooked is the accurate process representation in the model. Are we accurately representing the processes in our model? So by solving these challenges, we can increase the confidence in our model outputs, and then we can use those outputs more confidently for our Water Accounting Plus analysis and provide information that is accurate for decision making. But we know that one of the key challenges around modeling is spatial pattern representation with a good accuracy. Because traditionally, it's also spread across 4 dimensions.